Today, we'll work with R binom, P binom, and D binom. They're similar to R norm, P norm, and D norm, but the D binom works a little differently. First up is R binom. This will draw a sample of specified size from a binomial distribution. It's good for simulating binomial variables if you need to. The syntax is unfortunate. R has a bunch of these sampling commands, and they always use n for the number of samples they draw. But n is what everyone uses for the number of trials in a binomial distribution. R calls that size. So it's something you want to be careful about. Say 3% of eggs from a distributor are cracked, and a store has 60 cartons of eggs. Now, if these eggs are a random sample, like the eggs are cracked coming off a conveyor belt, and whether they turn up in a carton is totally random, then we could use the binomial distribution. But remember that independence is one of our assumptions. So if the eggs are being cracked because they're being knocked together, and cracked eggs tend to be close to other cracked eggs, then we wouldn't have independence. It's always something you want to check for with these distributions. But say we allow for independence. Then we want to see what the cartons might look like. Each carton has 12 eggs, so n equals 12. P equals 0.03. I'll run this, and the 60 cartons might look like this. A few ones, some have 2, but most have 0. I can run it again and again, and just kind of, you see this one had 3. Um, but I can change the P, so maybe 25% of the eggs are cracked. And now you see more eggs per carton are cracked. But that's the R binom, and it can be useful for modeling things. D binom gives me the probability that a random variable equals k. If I have 7 trials, the probability of success is 0.1 for each trial, then the probability of exactly 3 successes is 0.02296. P binom finds the probability that the random variable is less than or equal to k. With 7 trials and p equals 0.1, the probability of no more than 3 successes is 0.9973. If we have 8 trials and the probability of success is 0.3, the probability that x is greater than 2 is 1 minus the probability that it is less than or equal to 2. The probability of being less than or equal to 2 is p binom 280.3, so we subtract that from 1, 0.4482. That's the probability that x is greater than 2. When n equals 12 and p equals 0.45, the probability of 5 or more successes is 1 minus the probability of 4 or fewer successes. And that is 1 minus p binom 412.45. With this p binom, you have to pay attention to what points need to be subtracted. I'll do a couple of problems from the book. This is from the smoking question on page 152. You have 7 friends who smoke, and the probability that a smoker gets a severe lung condition in their lifetime is 0.3. Now, as they point out, if your friends know each other, they may influence each other's smoking habits, so our independence assumption would be violated. But let's say we can consider them a random sample from some population so that our independence assumption is justified. First, how many would we expect to get the disease? The mean of the binomial distribution is n times p. And here, n is 7, p is 0.3, and that's 2.1. We expect 2.1 of your friends to get the lung disease. The mean of a distribution is also known as its expected value. What is the probability that at most 2 of your friends get the disease? At most means no more than 2. 2 is included, 1 is included, so is 0. We would use p binom here, p binom 2, 7 trials, 0.3 success on each trial. 0.647. And note that this is the same as adding up the d binomes. So d binom 0, 7.3 plus d binom 1, 7.3. This is from problem 418. If 90% of people have had chickenpox as a child and you randomly sample 100 people, what is the probability that exactly 97 have had chickenpox? For exact probabilities, we use d binom. We have 97 successes, 100 trials, and the probability of success for each trial is 0.9. 0.00589. If you randomly sample 100 people, what is the probability that exactly 3 have never had chickenpox? If you think about it, that should be the same thing, because if exactly 97 people had it, then exactly 3 didn't. But let's change our p so that now success means not having chickenpox. So we'll have 3 successes, 100 trials, and the probability of success is now 0.1 because now a success is not having the chickenpox. And it's the same thing. What is the probability that at least 1 out of 10 have had chickenpox? Now, n is 10. Having chickenpox is the success, so p will be 0.9. And if at least 1 person out of 10 has had it, then the options are 1, 2, 3, all the way up to 10. The only way this doesn't happen is if 0 of the 10 got chickenpox. The answer will be 1 minus p binom 0, 10.9. And p binom 0 and d binom 0 are the same thing, but in general, you're going to want to use p binom for at least questions. Run this and I get 1. That means p binom 0 must have been pretty small. (10 to the negative 10th). So if you sample 10 people, the probability that at least one of them has chickenpox is nearly 100%. What is the probability that at most 3 have not had it? If we're looking for people who haven't had it, then success would be not getting it, and that means p equals 0.1. The probability of at most 3 is the probability of being less than or equal to 3, and that's p binom. P binom 3, 10, and success is 0.1 now.